Hello girls, welcome to video 2. So, if you watched the first video and was like, well, he did an awful lot of writing there. I don't think I really needed that whole study guide because he basically did it all. That's not going to be the case in this video. So if you don't have the study guide yet from Finalsite, please go and get it now. And the reason you're going to need it is this video is going to have a lot more talking in it than writing. There'll be some writing of answers, but a lot of this will be a lot more conversational. So you might find yourself needing to pause the video from time to time to write down what it is that I'm saying. We have, again, some essential questions, and just as important, we have some essential definitions. This is where we're going to start getting into the portion of the unit where we're going to start analyzing functions using some terminology that, even though some of you are familiar with lines and what we've been doing, you probably haven't done before. So feel free to pause the video at any point, maybe rewind to hear exactly what it was that I said. So the first essential question is, what does a graph represent? Now, if you look at the large print in the purple font, it says that the set of all solutions of an equation forms the equation's graph. So if I have an equation, any of those equations we graphed in the first video, if I needed a solution to those equations, there are, in fact, an infinite number of them. So if I had the equation y equals x plus 3, any solution to this equation will be a point, x comma y, that satisfies the equation. So say that x equaled 1. If x equals 1, then y equals, Ashley just yelled out 4 without raising her hand, and say that x equaled 0. Alex is raising her hand, and she would have said y would equal 3. So I found two ordered pairs easily by letting x equal 0 and letting x equal 1. There are an infinite amount of numbers that I could put in. Say that x equals 100. Then Catherine would say that y equals 103. So that's what I'm saying. We're getting a solution set. We're getting an infinite set of ordered pairs that will represent solutions to the equation. And then I can't write them all, so I can represent them on a graph. I know that when x is 0, y is 3. That when x is 1, y is 4. And way off up over there somewhere, when x is 100, y is 103. So when I plot this line, I'm representing an infinite number of ordered pairs that the line goes through, all of which are solutions to the equation. So like here, when y equals 0, x equals -3. All the points on this line are all solutions to the equation. So that's what it means to say that the set of all solutions of an equation forms the graph. The graph is the solution set. The same way that when you were graphing solution sets of inequalities, I had you graph them on number lines. The plane is just a pair of number lines, an x and a y axis. We're still representing solution sets. And after a little while, we'll still have hollow bubbles in here. But for now, we have all solid bubbles, so all of those values are included. So, when should the points on a graph be connected? How are functions analyzed? What is the difference between a line and a line segment? And how are intervals represented? A lot of these, with the exception of maybe the last one, are best learned the same way I learned to swim. You just get thrown in the pool. So let's look at the definitions that are listed in blue, the 5 definitions that are on the study guide. So the first one, the graph of many functions will cross both the x and the y axis, just as this one does. The points where it crosses are called intercepts. So right here at the point 0, 3, I see it crosses the y-axis. I call that point a y-intercept. And this is the output when the input is 0. Just as importantly, maybe more so, I have over here where it crosses the x-axis, giving me an x-intercept. This is the input value when the output value is 0. If I'm not moving up or down, I'm directly on the x-axis, making the output 0. So that's what it means to be an intercept. So when I'm trying to find a y-intercept, I'm going to say let x equal 0. I'll always have a 0 for my input value. And when I'm trying to find an x-intercept, I'm going to let y equal 0. I will always have an output value of 0. That's going to tell me exactly where on the axes these things are crossing. This is really important, especially when we're analyzing something in real life, something situational. A lot of times the intercepts are going to represent a beginning and an end to something. Okay, so that's going to be something that we look at as we start doing a lot more word problems. So next up, the next two definitions are maybe, if you were to ask previous students who have taken this course, the most headache-inducing, and I don't really understand why. They're not difficult concepts, but they're concepts that if you try to do a problem without thinking about the definition of these terms, it can be a little bit confusing. So the domain of a function is the set of all possible input values, anything that I am allowed to input into a function. The range of a function is all possible output values, anything that is a possible output. A good way to think about this, especially when it comes to range, is that inputs and outputs are directly related to what we talked about those first couple days. Independent variables and dependent variables. The output depends on what the input is. The range depends on the domain. The range depends on the domain. So let's just look at what we graphed here with y equals x plus 3. I'm thinking, what are all the possible input values? And maybe it's better to think the other way. Are there any impossible input values? Is there anything that breaks math that I wouldn't be allowed to input into this function? No, I can put whatever I want in for x. Put 0, 1, 100 billion, pi over 5, whatever I want. I'll always get a valid output value. There's nothing in there that's going to break down any part of the function. There's a couple of things that you know about mathematically that will affect range. That is when we're going to involve fractions where x is in the denominator and square roots where x is part of the radicand. So you know that there are going to be particular things that we're not allowed to have happen in there. We'll get to those when we get to the examples. Some other things that will affect domain and range. Context. Here I'm talking about not something like this where I just wrote an equation and you're like, y equals x plus 3. What's x? What's y? Who cares? It's just y equals x plus 3. But if I all of a sudden say that x is the number of hours and y is the number of tables, we're going to start thinking about, well, are there possible output values that aren't allowed? Like, can I have half a table? Does that make sense in the context of the problem? Maybe we're thinking about this in terms of people and the number of cars that we need. Can I have half a person? That sounds gross. Can I have 2/3 of a car? Yeah, but it doesn't really make sense in the context of the problem. So the two things that you're going to be thinking about when it comes to domain and range is that the range depends on the domain. Is there anything that is not allowed to be an input? And what's the context if